Hey guys, Dr. Brown here with Kubo Math, coming to you from Tarlac City, Philippines. Okay, I was asked a question a couple of days ago. What is a standard deviation? So let's jump into that, okay? I was in a class one time in an MBA program, and the teacher asked that very same question. What is a standard deviation? And one of the guys in the class said, well, it's the square root of the variance. And the teacher said, you are technically correct. Now what is that? He didn't know. He couldn't explain it in just a simple terms. And the teacher said, and this was awesome, I've used this through my entire career. He said it's how much the data wiggles. It's wiggleability. And I thought, I can remember that. And I've never forgotten that. All a standard deviation is a unit of measure of how much the data wiggles. Now you might ask, well, why do we need to know that? Oh, there's a book out there by Wheeler. It says, Understanding Variation, the Key to Managing Chaos. I would encourage you to read that. Everyone should read that, not just engineers. Every accountant, every manager, every CEO, everyone should read that, because it looks at wiggleability of data and how that impacts things. Now you might say, well, why does that matter? Let's assume you're an engineer and you design something and you say, well, this is the stress, and this is so many KSI or so many megapascals. I'm just going to use the letter or the number 1, okay? And you have the product you've designed, and it has a certain strength to it, and we're going to say that it's 4 times greater than the stress. So you would say, I have a safety factor equals to 4. And everybody would go, oh, it's awesome. Okay? What if we had variation about the stress, and we had some unit of measure, a distribution about that? What if we had a distribution about the strength? And by the way, we do have distribution of stress. We do have variation around that value. We do have variation around the strength. Guess what? The overlap of those two curves, that's the probability of failure. That area under those two curves where they intersect, that's why things fail. Now, I would assume everybody's bought a phone. Have you ever had your phone fail? Yes. That's because the stress was greater than the strength. Now it may be you dropped it. If you dropped it, wow, stress may have been way over here. But still, the stress was greater than the phone's strength. That's why everything fails. That's why cars fail. That's why the tires fail. That's why the lights go out sometimes. Things fail because stress is greater than strength. So for me, I ran reliability engineering groups. That's what my PhD is in, reliability engineering. And our entire function was understanding variation, understanding standard deviations and their impact on life of product. Let me grab another marker here. Okay, now there's all kinds of different units of measure of variation. One could be, let's say, range, for example. And all a range is the maximum value in your group of data minus the minimum. Now I have some numbers here, 10, 20, 12, 17, 16. Maybe that's the time to complete a task. That's the diameter of something, or how many hours something lives before it fails. Okay, maybe lights. for example. Okay, well, I could say the maximum number is 20. If you look through that data, 20, yes. And then the minimum number would be 10. So 20 minus 10 is 10. So the range of that data is 10. Now, that just deals with the extremes. I may not want to know that. So there's another interquartile range. Usually you're dealing with the inner 50%. And how that works is the ith order is equal to the percent of concern divided by 100 times n. So in our case, you put, to calculate this, let's put the data in ascending order. So the lowest one is 10. Let's see, I'll tick them off. 12 is the next one. 16, 17, and then 20. Okay. All right, so now I have it in an order, and we like to say that's my ith order, I, and usually they call this x sub I. All right, so I'm concerned about the inner 50%, so from 25 to 75%. So I could say, well, I equals P 25 over 100 times N, 1, 2, 3, 4, 5. So 0.25 times 5. 5 and 5 is 25, 2, 10, 11, 12, 2 decimals, 1.25. So the ith position for the 25% is 1.25. Well, I need to round that up to the second position. You know, it's in here at 1.25, but I don't have a value at 1.25. So round it up. Now I want to look at the 75% position. So 5 times 5 is 25, 35, 37, 3.75, so we'll round it up to 4. So these values would represent the interquartile range from 25% to 75%. It's the inner 50%. Okay? Now back to our original question. What is a standard deviation? You know, there's all kinds of calculations for things. If you know the mean of a population, it's denoted as mu. But if you may not know that, you may have to take a sample trying to figure out what mu is. Now, if you know sigma, that's the term for standard deviation of a population. Keep that in mind, of a population, and that equals the sum of x sub I minus mu, that's squared, divided by the population, and take square root of that. Now, most of the time we don't, in manufacturing and in design, we don't know what n is, and we may not know what mu is at all. I mean, at all. So this is not one I use very often. So I'm going to take it off the board here. We would use S, which is my sample, or sigma x bar. We would say this is my sample sigma. These are the same thing. And that would equal the sum from I equal 1 to n of x sub I minus x bar squared over n minus 1 and the square root of all of that. So it's a little different because now we're using the sample mean and then a degrees of freedom where we have n, which was our total sample size minus 1. taking the square root of that. Now obviously the variance is this number squared. And then the radical sign just actually drops off when you do that. In our case, what is a standard deviation? We're going to look at the standard deviation of a sample. Okay, let's take this data set and let's calculate a standard deviation for that. I'm going to write this, I guess I'll write it here, S All right, get ourselves a little bit of room here. All right, we have 12, 17, 16. Remember our order. Now it's not in ascending order now. Because it won't matter. X sub I. This is I. Now we had X bar. We have X sub I minus X bar. X sub I minus X bar squared. And then below that, we have the sum of X sub I minus X bar squared. Now you might be thinking, well, what is X bar? Well, X bar is the average. All right, if I were to add these numbers up, I get 75. Okay, so the sum of that column is 75. Okay, X bar then equals the sum of X sub I divided by N. So 75 divided by 5. So 75 is my sum of X sub I divided by N, and 5 is how many samples I have, and that equals 15. Okay, so now X bar is 15. My average is 15. Now, X sub I minus X bar. 10 minus 5 is a negative 5. Negative 5 squared is 25. 20 minus 15 is 5. 5 squared is 25. 12 minus 15 is a negative 3. Negative 3 squared is 9. 17 minus 15 is 2. 2 squared is 4. 16 minus 15 is 1. 1 squared is 1. Okay, we need to sum these up. 25 plus 25 is 50. 50 plus 10, 60, 64. All right. So what does that give me? The sum, X sub I minus X bar squared. So I have the square root of 64 over N, which was 5. 5 minus 1 is 4. Now I could rewrite this as the square root of 64 over square root of 4. And that gives me 8 over 2. And that equals 4. So my sigma, sample sigma, my sample standard deviation is 4. So what have we learned about that data set? We know X bar is 15, and we know the standard deviation for the sample, I could write that as S, equals 4. Now you may be thinking right now, well, big whoop. What does that mean? What do I do with that? Oh, lots of things. All right, let me clear this out. If this information came from a normal distribution, which means it looks something like that, it would be saying that my average X bar was right here, and what was that number? 15. Now the beauty of this thing is 1, 2, 3, 1, 2, 3. There's to the control limit of a normal distribution, its X control limits is x bar plus or minus 3 of those standard deviations of the sample. Oh, it's going to behave where it's just going to move around like that. Now the cool thing is there's 68.3% of the data plus or minus 1 sample standard deviation. 1 plus or minus 1. Now there's 95.4% at plus or minus 2 of those standard deviations. And 99, I may need to clear out here. X bar equals 15. Standard deviation for my sample is 4. Okay? So now 99.73% is plus or minus 3 sample standard deviation. There's power in that, because now you can begin to understand how things are going to behave. For example, if I have 15 and standard deviation was 4, what does that mean? This value right here is 19. This value here is 23. This value is 27. My upper control limit is 27. If a nuclear explosion is going to happen at this thing getting above a unit of 23, whoa, what's the likelihood of that happening? I can calculate that. We'll do that in future videos. Conversely, so 15 minus 4 is 11, 7, 3. So the control limits of this thing are 3 to 27. It's going to oscillate around in here. I mean, it's really cool. So anyway, what is a standard deviation? It's how much data wiggles. It's the unit of measure of wiggleability. Okay? We'll explore this a little bit more, because we need to look at standard normal tables, t-distributions. Ultimately, we want to work our way up to where we're doing hypothesis testing, which is a crucial thing for engineers or anybody for that matter that's changing from something to A to B. So where you can actually statistically evaluate, does it make sense to make the change or not? Okay, why are we doing this? Hey, together we're trying to build a better tomorrow and do that through math. Keep studying, guys. Remember, what is a standard deviation? It's wiggleability, a unit of measure of how much data wiggles. Okay, that's all for now. We'll talk to you next time. Thanks.